100 gigahertz, where we detect tens of molecular lines. So the scientific goals of this project is to elucidate the link between the star formation that occurs in such a molecular cloud and its structure, both its structure, its physical structure, its chemical structure, and its dynamical structure. And of course, star formation and GMCs are very complex and chaotic systems. So those questions need to be addressed in statistical terms. And we are trying to build an unbiased data set of a full GMC. And for this, of course, we need this kind of observations where we observe a lot of different tracers that will be sensitive to different components of GMC. You can see here the interest of observing in those radio domain. So here the image that I show statistical terms, visible image, and we are trying to build an unbiased data set of a full GMC. And for this, of course, we need this kind of image formed from the isotopologues of CO. It reveals all of the internal skeleton of the molecular cloud. And to get an idea of the size of this field, I show here the size of a full moon. So it's a very large field. So from this kind of data set, already just from accessing the data and having a quick look at it, we can already answer a lot of scientific questions that come to mind without using machine learning methods. So I will just quickly give a few examples. For instance, one very common question is how to estimate the mass of molecular clouds, because most of the mass of a molecular cloud is in molecular hydrogen, which is for most of it not directly observable. So people use indirect or trace component of the cloud to trace the total amount of matter, and they can use, for instance, CO emission or dust emission. And here in this cloud, we could easily study this and find that here it's actually the CO deduced mass that's higher than the dust traced mass. So contrary to the usual discussions about CO dark gas, here we have CO over bright gas. Another kind of thing that we could have a look at, for instance, HCO plus is very often used as a high density tracer in extragalactic observations, mainly due to its high critical density. So we can wonder whether critical density is a good criterion to define a high density tracers. And we see here with a very simple comparison of our map. So this is only part of our total map, but our map of HCO plus compared to the N2H plus map, because those two molecules have very similar high critical densities. In our observations, they have also similar peak temperatures over the whole map, but we see that the maps are completely different, with the N2H plus really highlighting the high density cores of the cloud, while the HCO plus emission is much more extended, and this is due to chemical differences, as HCO plus can be easily formed anywhere, while N2H plus is quickly destroyed by reaction with CO, so it mainly exists in regions where the density is high enough for the CO to freeze out on the grains. But one thing we have to keep in mind is that such an observational huge data set, not only it's massive in terms of the amount of data, we have around 1 million pixels, and for each pixel more than 200,000 spectral channels. But it's not only massive, but it's a high dimensional data sets. Whether we look at it in terms of spectral dimension, or if we reduce it to the detected molecular lines, we still have tens of detected molecular lines. So our data set lives in high dimensional space. And what we have to keep in mind is that what I showed before, we are mostly looking at projection of the data set on a few of its dimensions. For instance, scatter plot of two of our line intensities. But as you go to higher and higher dimension of the space, those kind of 2D projections contain more and more insignificant amount of information compared to the full information of the dataset, which is contained in the multidimensional ways different variables are correlated to each other. So this creates new challenges when we have to explore such high-dimensional datasets. And if you add to this the fact that the questions we want to tackle of understanding star formation in GMC is really a statistical question, we really need to move to modern statistical methods and, in particular, machine learning. So I will first present approaches using machine learning tools on the observational dataset, and then using the same kind of tool, but on modeling on model results datasets. When we have to deal with high-dimensional data, the first and simplest tool is principal component analysis, which is not a really recent tool, but which has known a kind of a revival with the advent of the big data era takes place now. So PCA, the idea of PCA is to analyze the correlation structure of a high-dimensional dataset and try to extract a few underlying factors uncorrelated from each other that can be sufficient to explain the correlation structure of the dataset. So here, if we applied this to our dataset, and we found that indeed we have one principal component that explain most of the correlation structure, and then a few more that explain much less of the dataset, but that are still significant. And this is understandable in astrophysical terms, as of course we expect that the more matter on the line of sight there is, the higher, to first order, the higher the line intensities will be, so that we expect that all line intensities to first order correlate with the column density of matter. So this first component that explains most of the correlation, we expect it to be related to the total column density of matter. And then what will be interesting are the next components that will start to highlight the chemical effects that make some lines sensitive in different ways to different physical or chemical parameters. And indeed, if we look at how the principal components are constructed, of course, PCA is a linear method, so all principal components are linear combination of the molecular lines that we observe. And if we look at those combinations, we see that indeed the first principal component has positive contributions from all the molecular lines, which is consistent with this explanation as a total column density. And then we see chemical effects starting to appear with, for instance, the second principal component having positive contribution from N2H+ and methanol, which are typical of very high density cores, and negative contribution to 12CO and 13CO, as in high density cores, those lines will start to be optically thick, and also those molecules will freeze out on grains. And in the third component, we see appearing a contribution of C2H and CN, which are known to be associated with UV illumination. So we can see that we can start to hope that our principal components are related to the physical parameters that we are interested in. And indeed, if we compare those principal components to independent estimates of those physical parameters, so to estimate the total column densities, we used dust emission, Herschel observation of dust emission. For the local density, this is a bit more complicated to estimate, but we took core catalogs that, at least for dense core, gave estimates of the density. And for the UV illumination, we used PAH emission. And we see that indeed our first three principal components are correlated with those three physical parameters of interest. Of course, the correlation is much better for the first one than for the second and third one. And this is to be expected, as principal component analysis is only a linear method, and we expect that the physics here is more complicated than this. But this gives already a first qualitative idea and allows to create some indicators of those physical conditions. And we see here how we can create a synthetic image where the brightness encodes the total column density of matter, and then the color encodes the density and the UV, so that you can easily see the regions that are, for instance, dense and not UV illuminated, that will appear in blue and dark blue, and the regions that are, for instance, the PDR that are dense and strongly illuminated, that will appear in red or orange if they are at lower density. So Of course, the main drawback of principal component analysis is that if you have in the physics nonlinearities, different physical or chemical regimes, of course, PCA will not capture them and will only give some average result over those different physical and chemical regimes. So we tried to see if we could separate different physical and chemical phases in our GMC map. So I want to emphasize that here what we are trying to do is different from previous approaches of GMC segmentations. Previous approaches have focused on separating spatial components of the cloud, so regions that might not be different physically in terms of physical conditions, but that are distinct because they are separated by regions with less emission. So people have done this using single molecular line maps or PPV cubes and clustering based on the spatial or spectral contiguity of the emission. Here we are trying to group together pixels not because they are close to each other spatially or spectrally, but because they have the same similar molecular emission and using multiple molecular lines. And so this is what in machine learning we call a problem of clustering. So to understand what's clustering analysis, the idea is to try to find natural categories in the dataset to see if our data points will tend to naturally group themselves in different categories, so that without a priori, this is what we call an unsupervised approach, without a priori, we can see if our data already tells us that different categories exist. A very simple example to understand this is to forget for a minute about giant molecular cloud and come back to one of the first scatter plots that we see when we learn astrophysics during our studies, an HR diagram of the luminosity and color of stars. When you see this, even without any knowledge, you immediately see that there are at least 3 groups of points that naturally distinguish themselves. And we later learned that the long one in the middle is correspond to main sequence stars. There are giants and white dwarfs at the bottom. Of course, what we did here is clustering by eye. This is very easy to do in this case. So yeah, what I want to emphasize is that this really highlights the fact that the patterns in the dataset, the way the points groups themselves can bring some insight into the physics. Here, we know that those separations are related to different stages in the life of stars. But here, it was easy to do by eye because this dataset is in 2 dimensions. As soon as you move to high dimensions, it becomes very difficult to identify those separate groups by eyes. And this is why we need machine learning algorithms, a special category that is called clustering algorithms. So here we used one of the different clustering algorithm, which is called mean shift algorithm, which tries to define clusters based on the maxima of the probability density function of the dataset in its high dimensional space. So we first applied it to a reduced a low dimension version of our dataset using only the 3 isotopologues of CO, and already we see some interesting results. The clusters that appear, when we compare them to independent estimate of the density of the gas coming from dust emission, so information that the clustering algorithm has not seen, we see that our clusters, the 3 clusters on the PDF figure at the bottom, the 3 clusters represented by 3 peaks of different colors corresponds very well to the 3 peaks that are present in the PDF of the gas density, and that those peaks correspond to the usual empirical definition of diffuse gas, translucent gas, and dense gas. So we see that just based on our dataset and just on the observation of CO isotopologues, we already see that there is some empirical basis on, in defining those 3 categories of interstellar medium. So we then move to adding more dimensions, more molecular lines, taking all the lines that are detected on a wide region of the map, so adding HCO plus and CN. And what we saw here is that in addition to distinguishing different density regimes, we see also a distinction among the high density regions. So we see this distinction between blue regions and orange regions. And if we look at where the orange regions are located on the map, we see that they are located mainly around the two known star-forming region in this molecular cloud, NGC 2023 and NGC 2024, and on the edge at the right on this image, which is the edge of the cloud that's illuminated by the Sigma Orionis star, which is located outside of the field of view here, but which corresponds to well-known PDRs in this region, especially the Horsehead PDR that's at the head of the Horsehead Nebula. And this distinction of the orange cluster compared to the other clusters, we can understand it by looking at those figures to the right, which are probability contour plots of the probability density function projected on pairs of lines, so CN and C18O for the first one, and CN and HCO plus for the second one. And we see that this orange cluster is characterized by overbright CN, also overbright HCO plus, which I don't show here, but also higher than usual CN over HCO plus ratio. So we tried to understand whether this was due to excitation effects or to chemical effects. So for this, we compared to Radex models that would explain the parts due to excitation and radiative transfers in order to deduce typical value of the column density ratios in those clusters. And we see that indeed the variations that we found between the different clusters are related to the ratio of the UV illumination, which is the G0 parameter over the density of the gas, so that we indeed have chemical enrichment both in CN and HCO+, that's related to the illumination by the UV field. So what we have separated here with our clustering analysis is two really distinct regimes in interstellar chemistry, which are photochemistry, where the chemistry is driven by UV photons, and shielded gas chemistry, where the chemistry is mainly driven by cosmic rays. So both of the approaches I've presented so far are unsupervised. We don't have the answer in advance. We don't know, for instance, here the categories that we expect to find. And we try to see if there are interesting patterns in the dataset. But this is only part of what machine learning has to offer. And another part of machine learning that's maybe even more known than unsupervised approaches is supervised approaches, where you have a specific question, you know the quantity you want to predict, you have some examples where you have measurement of this quantity and you want to learn to predict this quantity. I will show an application to one specific question, which I said a few words about at the beginning of the talk, which was estimating the total mass in a giant molecular cloud. So as I said, most of the mass in a giant molecular cloud is in the molecular form of hydrogen, H2, which is almost impossible, at least for most of the bulk. For the bulk of the gas, is impossible to observe. And so the way the total quantity of matter is usually measured is most often using the fact that interstellar gas is mixed with dust grains with roughly at least constant abundance ratio. And those dust grains emit thermally in the infrared, so we can observe this emission and deduce the total quantity of gas. Of course, the limitation of this is that to observe the infrared domains that we need space telescopes, for instance, Herschel, and we don't have them anymore currently. Other approaches rely on using trace molecules of the gas, in particular CO, using the assumption that except for the surface of the cloud, in a molecular cloud, all of carbon will be locked, at least all of the gas phase carbon will be locked in CO. And so CO should be a good tracer of the full mass of the molecular cloud, the full quantity of matter along the line of sight. So what's done usually is using a simple linear scaling with a XCO factor. We see that when we apply this to unresolved GMCs, this seems to be a pretty good assumption. But when we look at a resolved molecular cloud, for instance, here our Orion B dataset, it's much more complicated. The relationship is not at all linear. There are saturation effects at high intensities and so on. And so this simple linear scaling is a bit is not enough. And what gives us hope that we can do better is that we saw that with PCA, so when we don't limit ourselves to one single molecular line, but we use tens of molecular lines at the same time, we could build a linear combination of those lines that was very well correlated with the total column density of gas. But of course, this relationship was not perfect, and we expect that with a machine learning model that can capture nonlinear behavior, we might be able to do even better, combining nonlinear behavior and multiple molecular lines. So this is, of course, a typical regression problem where we want to predict a quantity, here's the total column density of gas, based on different features that will be here, the line intensities, the integrated intensities of different molecular lines. So the machine learning tool that we used is called random forest. I will very quickly explain just the principle of it. It combines two ideas. The idea of decision trees, which is a very simple model, regression model. It can also be used for classification, but here we use it for regression, where basically you can think of it as you start from the average value of the quantity you want to predict on your dataset, and based on a series of binary decisions based on your different features, you will add or subtract to this value to end with a different possible predicted value based on this. So basically, you have a binary tree of decisions that ends at a leaf, and this leaf gives you a predicted value. So it's a very simple model, and in order to make it very flexible, you need to have very deep trees with a lot of levels. And if you have very deep trees, then those trees are very prone to overfitting, where you might start to learn the noise of the dataset. So this idea was combined with another idea to tackle the problem of overfitting, which is bagging. The idea is that if you combine many different models that each make large errors because they are strongly overfitting, but if those errors are uncorrelated between your different models, then when you average over all of your models, you get a very good answer. So in order to make those, so the critical point is to have uncorrelated errors between your different models. And in order to have this, the idea in random forests is to use for each tree a bootstrapped sample. So a sample drawn with replacement from the original dataset, so that each tree doesn't see all of the points of the dataset. So the trees have seen different part of the dataset. And you also add something that each tree only use a random subset of the possible features. So you put randomness in the way you build the different trees so that their errors are independent. And then when you take the average, you obtain what we call a random forest. So those models are very powerful, very flexible, but much simpler to use and faster to train than heavier models such as artificial neural networks. And they also have an advantage that they are more interpretable because the decision trees on which they are based can be more easily accessed and interpreted. So the way we apply this to our dataset, so here we will use the molecular lines. So we will use 32 molecular lines, and for each one we use both the integrated intensity and the peak temperature because both can bring slightly different informations. The quantity that we want to predict is the total quantity of matter, and in order to train our model, we need to have the answer on the training set. So for this, we use total quantity of matter derived from dust emission observed with Herschel and Planck. So we have to keep in mind that we are learning dust-based maps. So if there are biases in the way dust emission traces, in the way the total column density of matter is derived from dust emission, we will learn those biases, but this is the best we can do so far. And we split our dataset in the grid that I show here. We train our model on all of those squares except the square around the Orsed, and we then test the efficiency of our model on this last square that is centered on the Orsed nebula. Of course, in the paper, when we do the accurate estimation of the precision of our model, we repeat this for each of the squares, which is a procedure called cross-validation. But here I will only show the result for simplicity when tested on the Orsed nebula. So first, if we compare what we get with a simple multivariate linear regression based on all of our molecular lines to what we find with this random forest models, we see that with a multivariate linear regression, we had something that was already pretty good, which is what we expected from our PCA analysis, but with significant biases that we see that there are significant. So on the left panels, what we see is the predicted column density compared to the actual column density. So the predicted value compared to the truth. So a perfect prediction would be all lined up on the central diagonal. So we see significant biases in the case of multivariate linear regression. And with random forest, we see that we get a much better prediction with almost no bias. And root mean square error on the logarithm, that's equivalent to an error factor of 1.2, so around typically 20% of error on the prediction of the total column density of gas. The interesting point with random forest is that we can take advantage of their interpretability and try to understand how this prediction is made. The first thing we did is estimate the permutation importance of each of the molecular line in this prediction. So the permutation importance, the idea is that you take your initial data set and then you take one of the molecular line, you randomly shuffle their values so that you keep the same distribution, but you lose all relationship between this molecular line and the quantity you try to predict, and you retrain a random forest on this, and you see that, of course, this random forest does much worse than the initial one, and the loss in performance gives you a measurement of the importance of this molecular line for predicting the total column density of gas. So here, doing this, we found that there are actually 4 species that are really that are the most important, and which are the 3 isotopologues of CO and HCO+. And indeed, you see on the right that if now you train random forest models on an increasing number of lines, including an increasing number of lines. So as you add more lines, the performance of the model increases. So the error that you make decreases. And you see that after roughly 4 lines, you don't gain anything by adding more lines. So those 4 lines are already giving all the information you need to predict the total column density of gas. And you can do even more. With random forest, using the tree structure of your model, you can, for each pixel, estimate the contributions of the different lines to the prediction. And so you can do maps of the contribution, for instance, here of 13CO, which already we see that it contributes in most of the Orsed. When you look at 12CO, in contrast, it contributes mostly in the surrounding, so at the edge of the cloud, which is expected as 12CO quickly becomes optically thick as you go to higher column densities. So it will bring information mainly on the surface of the cloud. C18O will contribute mainly in the dense regions, and HCO+ we find it to contribute in a broader halo or envelope around the cloud. So what I presented so far were application of machine learning methods to the observational data. I will move in this last part to an example of what we can do with machine learning method when applied to data sets that result from astrophysical models. So for this, I will show a work that we did on a very specific question, which is how to estimate the ionization fraction in the interstellar medium. So the ionization fraction, which is the abundance of free electrons in the gas, is very important in the physics and chemistry of the neutral ISM, because it controls several key processes. First, it allows fast ion-neutral reactions that will drive the development of complex interstellar chemistry. It will also control the coupling of the gas to the magnetic field, which will have important dynamical effects, for instance, during the collapse of prestellar cores. It will also affect the efficiency of photoelectric heating, which is one of the main heating mechanisms in the ISM. And it will affect the way we interpret the emission of some tracers, because high dipole moment molecules, such as, for instance, HCN, will be very sensitive to collisional excitation with electrons. And so the knowing if we don't know the ionization fraction of the medium, we might make big errors in the way we interpret the emission of those molecular lines. So in giant molecular clouds, this ionization fraction will vary by orders of magnitude, depending on how close we are to the ionizing radiation of stars. So if we are very close to young stars, everything is ionized, so the ionization fraction is around 1. As you go deeper into the cloud, all the photons that can ionize hydrogen have been absorbed. So now you can only ionize carbon, which will provide an ionization fraction of around 10 to the minus 4. And as you go deeper, all ionizing photons are progressively absorbed, and you go to very low values of the ionization fraction that are maintained mainly by ionization by cosmic rays. And you can go down to typically value of around 10 to the minus 6 to 10 to the minus 9 in cold, dense gas. So now how can we observationally measure the ionization fraction in giant molecular clouds? Direct observation of the main charge carrier is very rarely feasible, except in very specific regions. For instance, here it was done in the PDR front at the surface of a cloud, but this is not applicable to a whole molecular cloud. And so most methods will involve indirect chemical tracers, which are a species which are affected usually by, for instance, recombination reactions, so reactions with electron, so that their abundance or the abundance ratios between two species will be sensitive to the fraction of electrons and will eliminate as much as possible the influence of other physical parameters. So the most common of those traditional methods is to use the DCO plus over HCO plus ratio, because this ratio traces the H2D plus over H3 plus ratio, so the deuteration ratio of H3 plus. And this ratio is enriched at low temperature because of this reaction. H3 plus HD will give H2D plus H2. But this enrichment will be limited by electronic recombination, so that the H2D plus over H3 plus ratio will be sensitive to the abundance of electrons, and the DCO plus over HCO plus ratio as well. So based on this simplified reasoning on the chemical network, people have proposed, so this is the relationship proposed in Caselli et al., which depends, of course, on the depletion level of the gas. If we compare this to a grid of chemical models, of course, the values are a bit different because the analytical relationships is pretty old, and the rates of reaction are known much more precisely now, but the trend is the same. And what we see is that what limits the use of these tracers is that it depends not only on the depletion factor, but also on the ortho-to-power ratio of H2, which is itself a very difficult quantity to measure in observations. And in addition, we see that at low ionization fraction, the slope of the relationship becomes very steep, which means that a very small error on the observation of the DCO plus over HCO plus ratio will result in a very large error on the estimation of the ionization fraction. But before all those limitations, there is one that's even more obvious. If we look at our data set, the detection mask of DCO plus covers only the densest cores, so that this tracer in any case can only inform us about dense core. If we want to have a global view of the ionization fraction in a giant molecular cloud, we will need other tracers. So the way, and the idea here is to use model to find other tracers of the ionization fraction. The way we usually use models and in comparison with observations is that we have observations of some molecular lines. We compare them to model to see which region of the space of physical parameters of the model can explain the observations. And then we do this at each of the pixels of the map, and we deduce for each pixel the values of the physical parameters. But if the lines that we have observed do not give enough information on the physical parameter that we're trying to constrain, we might have very badly constrained or degenerate values of our physical parameters. So here the idea is to go in the other direction. We start with a large grid of astrophysical models that explore all the possible values of physical parameters. And from this, we try to deduce which molecular lines will be the best tracers of a given physical parameter. Here it will be the ionization fraction, in order to be able to plan for new observation or to exploit existing data sets. So the idea is the following. We know that there is a relationship between our observable quantities, the molecular lines, and the target physical parameter, the ionization fraction. But we also know that this relationship will be affected by other unobservable parameters, for instance, the density, the temperature, or the UV field of the medium. So we will consider those other unobservable parameters as a source of noise. They will create some scatter in the relationship between the target physical parameters and so here it's an abundance ratio. And so what we will do is that we will create a model grid that samples randomly over all the unobservable parameters. And here, in order to use the minimum amount of a priori information, we sample uniformly over all the other unobserved physical parameters. And now, so we have a model, we build from it a data set sampling all possible unobservable parameters. And from this, we just need a way to estimate the predictive power of the different observables. So first, let's start with our grid of physical models. So we used a stationary chemical model with a full chemical network, including more than 300 reactions and 300 species, and 8,000 reactions, and exploring the range of realistic values in gas density, gas temperature, UV illumination, and so on. So you see here the list of parameters that have been explored and the range that have been explored. And we have defined two separate grids because we don't expect the same observational tracers to be the best tracers in very different conditions. So to make the problem a bit more easy to solve, we separate two different types of medium, dense gas and translucent gas, and we explore the range of possible values of the parameters for those two types of medium. We then selected species that we can detect in our Orion B observations, and what we will use as feature will be ratios of species. So either abundance ratios or line intensity ratios. So in order to have line intensities, we also post-processed the results of our chemical model with RADEX models, which compute the excitation and the radiative transfer. So now, how do we estimate the predictive importance of each of those ratios to find which are the best? So the idea is that we train a regression model separately on each of the ratio, and we use the quality of the prediction as an estimate of how good this ratio was. And the type of model that we used is, again, a random forest that I presented before. So we apply this. So here are the kind of results that we obtained. So first, on the left, what I show is the ranking of the different abundance ratios ranked by order of the quality of the prediction. So here it's measured using the R-square coefficient, which gives an idea of how much the variance has been reduced when going from the initial variance of the dataset to the residual variance. So value of 1 would mean perfect prediction, and then it decreases to 0 as the quality of your prediction decreases. So we see that we find a lot of abundance ratio that can give very good prediction, that can explain more than 80% of the variance in the ionization fraction. And you see on the right scatter plot of the ionization fraction versus two of those best ratio, and we see that indeed there is a very tight relationship between the ionization fraction and each of those abundance ratio, and we can understand why those specific abundance ratio appears. We see that a lot of the best ratios involve C2H, which is known observationally to be related to the UV field, because it's formed by carbon that's not locked in CO, and so that's still in the form of C+ or atomic carbon, and this requires the presence of UV. And of course, in translucent gas, UV photons will be the main source of ionization, so C2H will trace the ionization fraction. So in dense gas, we see very similar results. I won't enter into the detail here, but what we can note is that despite having variation by several orders of magnitude in several key parameters, the gas density, the auto-to-power ratio in our model grids, we find a relationship with relatively low scatter between some of our best abundance ratio and the ionization fraction. And the result, when we move to line intensity ratios, so using Radex post-processing, we still find line ratios that have similar, slightly worse, but mostly similar quality of predictions. So this means that indeed excitation and radiative transfer induce a bit of loss of information, but not so much. So line intensity ratios can be very efficiently used to predict the ionization fraction. The last thing we wanted to study is to understand the effect of noise, because of course our model grid didn't include noise, and some of the lines might be very good predictors, but might not be observable because they might be below the sensitivity limits of observation. So we studied how the quality of the prediction of the fit decreases when we increase the level of noise by artificially adding noise to our synthetic observations, and this way we could see that some of the some tracers that were not among the best could, at high noise levels, become the best tracers. So what we show here is the evolution of the fit quality based on each of those line intensity ratios when we increase the noise level, and we see that, for instance, 13CO over C18O, which at negligible noise level is not among the best tracers, becomes the best tracer. So this is the red line on the left figure. And based on this, we could provide a recommendation for tracers of the ionization fraction, both in the translucent gas and dense gas, for high sensitivity observation and for low sensitivity observations, but I won't enter into the detail. And the last point is that because random forest models might be a bit difficult to communicate to observers, they would be in the form of files that are dependent on some libraries. We also built simpler analytical fits of those relationships using polynomial fits with some saturation, so that we could provide the fit coefficients in a table that could be easily used by observers to deduce the ionization fraction from those ratios, those best ratios of molecular lines. So to conclude this talk, what I tried to show here is that new methods are needed to exploit the kind of massive and high-dimensional data sets that we have, and that we should not forget that we have massive and high-dimensional data sets, not only from observations, but also from model grids. We saw that machine learning tools indeed provide promising solutions to tackle the challenges that are brought by those massive data sets. And I tried to show also the difference between unsupervised learning methods that were very useful for exploratory studies, where we don't have a specific type of question in mind, but we want to see if there are noticeable patterns in the dataset that might be interesting and that might bring insight about the physics and chemistry of those giant molecular clouds, and supervised learning methods that are very powerful tool when we have a specific question in mind and some examples for which we know how to solve it. And in the case of model, we saw that we built a very general method to find the best observational tracers of any unobservable physical variable. So this method could be applied to different kind of model grids, PDR models, time-dependent chemical models, and to the question of predicting other unobservable physical variables. And so all this method is implemented in a Python code that's publicly available, and I give the address here. And this method is now being applied to our observational datasets for Orion B, and this will be the subject of a next paper. Thank you.
Thank you, Emeric. So, questions?
Well, I have a question, if I can ask.
Yes, sure.
In fact, you said that you had a very good information density with those machine learning methods. And I was wondering if you can have also some feeling of the metallicity variation inside the Orion cloud, because of course the dust to gas ratio should depend on metallicity, and when you are very close to the star, it's possible that the yield of star have more metals, so you could have gradient of metallicity. So have you been seeing this kind of metallicity variation inside the cloud with this method?
So far, well, not with this method, but even in the other studies that we did here, I focused only on the studies that we did using machine learning. But of course, there are more papers in this project that use different kind of statistical tools. And this is, well, so far we haven't been able to show differences in metallicities. It's a bit difficult because, of course, there are always chemical effects. For instance, if we see variation in the ratios of 13 CO to 12 CO, we have to disentangle chemical effects from variation in the elemental abundances. And so far, I think everything we have found was more related to chemical variations than metallicity variations. Mm-hmm. But it doesn't. We cannot exclude that there are some variations in metallicity.
And also, I was surprised on the fraction of ionization. There was no the DCO plus of HCO plus, which was in the old times a very good indicator.
Yeah.
It was not a good indicator here.
So the reason we don't find here, we don't find it with our methods, are in part explained by this graph, where we see that actually there is a lot of scatter in the relationship between the ionization fraction and this ratio. And with looking at the model grids, we see that we find that most of this scatter is due to the ortho to power ratio of H2. So if we could determine observationally the ortho to power ratio of H2, then it might be a better tracer. But also much more simply because it's only usable in a very small subset of our data set. So on all other points, it's unusable, and other tracers are usable, so they are much better.
Okay, thank you.
Emeric?
Yes.
Yes. About the third part of your work, I wondered, so you're using the other physical quantities as noise, like nuisance parameters and sources of noise. Mm-hmm. And I wonder if you tried, is this one trained on models? Is that right?
Yes, this is based on grids of chemical models.
Did you try at all to have the method predict not only the ionization fraction, but also, for example, maybe the temperature? And if you predicted two quantities instead of one, you might reduce the scatter in the and have a more accurate prediction of the ionization fraction?
Well, so we have, separately, we have started to try applying this method to predicting other physical parameters. And well, we see, for instance, that actually ionization fraction is one of the parameters which we can best predict from those chemical species. But the idea of predicting several of those parameters at once, we haven't tried yet. No, I'm not sure I would expect a gain in doing this.
Well, if you consider that the scatter that you have is due to the action of the other.
Yes, but what I mean is that if in the observable quantities we have information that allow to deduce, for instance, the density, then this observation should already be used by our random forest model when predicting the ionization fraction. Maybe it would be maybe it would be clearer to think of it in the context, for instance, of neural networks. If you can build a neural network that predicts the density, then you could build a neural network that includes this as a subpart to predict the ionization fraction, meaning that if you have a large enough neural network, when training it, it should be able internally to extract the information it needs to get the ionization fraction. So in theory, the fact of predicting two variables at once should not improve the performance, but in practice, of course, because the models are not perfect, it might happen that.
No, you're probably right. Yes. Yeah. Okay. Thank you. And if no one else wants to ask another question, you said you flashed it very fast that you needed only 5,000 models to train in a 7 dimensional.
So this was something we deduced from our study. So here, actually, the plot on the left where I show the ranking, the estimate of the R-square coefficient, we don't see it on this plot, but there are error bars estimated by bootstrapping, and we see that they are negligibly small. They are actually as small as the symbols we use for the points. Which shows that with our 5,000 model grid, it was enough to constrain this information. And actually, the reason is that despite having a 7-dimensional parameter space, the thing that we are trying to learn is actually lives in a 2D space of ionization fraction versus 1 ratio. And that's why a relatively small grid is enough.
And just to know, how did you sample it?
The grid, the model grid. So the space of physical parameters, as I said here, where was it? Here. Yeah, I sampled with a uniform distribution over a range of realistic values of each of the parameters. The reason for this is that this is the least informative distribution that we could use. Now, if we have more accurate information about the distribution of the physical condition in the interstellar medium, especially the correlations between the different parameters, we could include it in building a grid that respects this distribution, and this might give more accurate results.
I agree that it's the least informative, and maybe since you, in the end, you project on 2D, it's okay, but in 7D, using a random sampling with 5,000 models, you have a huge amount of noise. So somehow it works because in reality, there is only a 2-dimensional relevant subspace.
And yes, I think it works because for chemical reasons, those tracers, those ratios are very tightly related to the ionization fraction. Yeah. But what the idea here also is that what we expect is that this is kind of a worst case situation when we take the uniform distribution. If we find a predictor that works well everywhere in this space, then if we have any more accurate distribution that would be more peaked in some subregion of the space, it should at least work as well as the initial one. So what we might find is that some of the ratios that here were not identified as good tracers might, if we used a more realistic distribution, become good tracers. But we expect the good tracers that we find will remain good tracers.
Yeah. But what I mean, I don't criticize at all the fact of using a flat distribution. That's very logical. But then you when you sample it, you inject a lot of Poisson noise.
Yes.
And methods like Latin hypercubes or stuff like that may help somehow. If you discretize your grid and then use that, you may reduce some sort of noise. But again, since in the end, it all comes down to a 2D relevant subsurface, then you're good enough with 5,000.
Yeah, I think one thing I should precise in what I said is that indeed, what we find here is that it's sufficient when estimating so the R-square is equivalent to the root mean square error. So for the root mean square error, it gives already a good estimate with 5,000 points. Of course, if we want to have an idea of the maximum error that we can make, this will be very badly estimated with only 5,000 models.
Okay, thank you.
Any more questions? Well, I have a small question about the detectability of those line ratios. Can you wait? Well, this is for data which are very easy to detect. Now, if we imagine observing more distant objects, would the line ratio be indistinguishable between each other, because of the weakness of the signals?
Because of, sorry, I didn't.
Weakness of the signal or of the noise, of the signal to noise ratio. Because they look very close, in fact, to each other.
You mean in where do they look very close? You mean in the rankings?
Yes.
Yeah. So indeed, in those rankings, the precise ordering, I mean, it is not very relevant. What's important is that, for instance, here we have roughly 10 tracers that are above 80% of explaining 80% of the variance. So those are good tracers. Then, of course, the precise ranking could vary a bit. But I think in what you say about observing more distant regions, of course, then the noise level related to the signal to noise ratio might be lower. But I think what would be even more important is that then the beam would be larger, and we would mix emission coming from very different regions. And this is a much more serious problem, I think, because then it becomes very difficult to interpret this from physical models, because it's a mixture of emission coming from dense gas, diffuse gas, PDRs. So here, all the work we did was assuming that we resolve at least as well as we did in Orion B.
Okay, maybe I'll ask you the question I asked before about the when those data will be public. Maybe you can.
So the first square degree, which is basically what you see, for instance, on the map on the left. So it's not the full map. This should be public very soon. And for the full data set, I don't remember. We are finishing the observations now. So I think then there is a proprietary time set by IRAM, which is of, I don't remember how much, maybe 1 year, or maybe someone knows.
Okay, thank you. Well, I think there is no more question. So thank you very much again, Emeric. So the seminar will be put on the website so that you can share the link if you know interested people to look at this seminar. And and I will send the announcement for the next seminar, which is not yet fixed exactly. Let me check if I have the list with me. It should be Victor Bonjean in 2 weeks from now, and I don't have the title yet. So see you in 2 weeks.
Bravo.
Thank you.
Merci. À bientôt.
À bientôt.